everyone. My name is Maggie, and I'll be your host for today's webinar, Modernizing T&E Flight Test Execution. Today's webinar will be delivered by Chito Parang and Joe Murphy. Joe's the Integrated Solutions Director and an aerospace engineer. He's been with AGI for 23 years. Chito is a systems engineer supporting Southern California and the West Coast T&E activities.
Okay, thanks, Maggie. Again, I'm Joe Murphy. I've been with the company for 23 years and really doing a variety of things here, most recently supporting and bringing a new solution set to the T&E community. A little bit about AGI. AGI is a company that provides physics-based modeling tools to the aerospace and defense community. 29-year history of providing these tools. There's a wide variety of uses across the air, land, sea, and space systems, across the life cycle of systems from design, development, test, operations, analysis. And really, the primary mission of the company was to create and provide tools and solutions which can dramatically improve the efficiency and effectiveness of aerospace and defense community. And it's really been with great results. The effect on engineering tasks is such that many of the things that people can do with our tools that used to take hours can be done in minutes. Things that used to take days can be done in hours, and weeks to days, etc. And so, and over time, we started looking about 8 years ago, and somewhat prompted also by policymakers in the community that were calling for smarter test and evaluation techniques. We had a lot of folks that were using our software in the test community for lots of disparate use cases. And I really started looking at how to produce a tool set that could provide a holistic use across the life cycle of test, and really concentrated specifically on the execution phase of testing, detailed test flight planning, test execution, and post-test analysis. And really all of that was focused around a set of particular challenges that are somewhat unique to testing. The test community, more and more has complex systems for both systems and software, and that means that test point narratives and test cards are harder and harder for SMEs and flight test engineers to derive proper test point narratives and execute proper test point geometry in sequence test cards. I say efficiency of tests here. Test point density is many times what it's expected to be based on current methods and the norms, and we found that test point density can be improved quite a bit. Refly rates are very high, 30 to 50%, although often caused by hardware, software, and other system and programmatic issues. Oftentimes they're also affected by less than rigorous detailed plans, which can lead to not achieving on-condition geometry and timing. Modern systems tests have larger and larger quantities of data, much of which goes without being fully analyzed. It's often hard to mine test points out of these large quantities of data. It's necessary more and more to combine lots of different disparate sets of data together when doing post-flight analysis and verification. And test teams are often challenged when it comes to communicating system capability along with test point completion. We had a meeting some time back with Dr. Gilmore when he was the DOT&E director, when we were supporting the F-35 program, and he lamented that he gets report after report of test point completion, but would like a way to assess the state of capability attainment or the evolution of capability. And so that, again, becomes a significant challenge. These challenges are all the more important given the high cost of testing. Cost per flight range from tens of thousands of dollars to upwards of $1 million a flight for complicated tests. Anomalies and unexpected difficulties sap resources and add to delays. And programs, when they get to the test phase, are often over budget, so the test phase is under pressure to hit milestones and control cost. Test programs tool sets are often custom developed for each test team. and we've seen them to be labor intensive to produce, sometimes late to completion, usually lack flexibility and interoperability between mission systems IPTs. Many times these tools are orphaned as authors of them leave the test team, and they become difficult to maintain and or have to be recreated. We also took note some time ago that for years, most of the disciplines in engineering have enjoyed years and years of maturing CAD, computer-aided design, and computer-aided engineering tools, where test has largely had to rely on traditional methods and has not gotten the same kind of attention by these tools makers. And this isn't a knock on test, but we've seen test groups using a lot of traditional methods when it comes to the nuts and bolts of putting detailed test event plans together, designing test point narratives, assessing the viability of those narratives, turning those into sequenced and choreographed test points that can be flown in test cards on the range. And that gets all the more difficult when having to weave together test points of lots of different disparate mission systems on the same flights. So what we are showing folks is a way to use a physics-based modeling environment in this commercial off-the-shelf tool set of SDK, characterize those systems to various levels of complexity, and then having characterized the system, allow them to fly it around inside this virtual environment and assess the relative value of the routes being designed. And then there's a whole host of output in the tool set that provides feedback to the designer or the post-flight analyst or whatever the user is at whatever stage they are, in order for them to properly assess what's being done in the tool. Over the course of 29 years, these capabilities in the tool have been matured, and within SDK and within the T&E Toolkit bundle, there are route planning, sensor modeling, communications, link and radar link and RF modeling, route parametrics, EOIR modeling, etc. This is brought together in a way that we can utilize it to support planning, operations, assessment, analysis, verification support, etc. We'll begin by looking at the detailed flight test planning aspect of that. First part of that is that within the tool set, there's a product called Aviator that allows you to characterize the performance of an aircraft. And once having that performance model, you can click out routes inside the tool, and the aircraft will fly appropriately. So if you click out a route, you can tell how much fuel is going to be used for one route versus another, or one sequence of test points versus another. That, together with the modeling, as I described in the previous slides, can all come together and provide a flexible and interactive environment to a flight test engineer, in which you can lay out a route and then assess the relative value of that route against requirements. So in this case, I'm looking at a simple route that's been laid out in an aspect angle to an emitter. And any of the things in SDK, the hundreds of different calculated parameters that you can get, can be hooked up to the route to show the relative value of that route against your objective. In this case, I'm just looking at aspect angle, so we're colorizing the route by aspect angle. And in a sort of CAD or CAE-like fashion, I could activate that for edit and drag that around. And as you drag it, you see the calculation change for the particular value of interest, in this case, aspect angle. So you can design that route to meet the condition that you care about, and you could stack up multiple conditions, multiple satisfaction, multi-constraint satisfaction conditions to determine what exact route is going to give you on-condition geometry and timing. So in the hands of a competent engineer, flight test professional, and over time, this would allow folks to design more test points into the green space of their route designs, and perhaps even harvest other parts of the route, ingress and egress, coordination holds, refuel weights, and that sort of thing, while assessing angles and performance conditions to targets, air targets, ground targets, etc. These we've seen directly that this can have an impact on effectiveness. This isn't to replace the smarts that folks have when coming up with route designs, but it can be injected at several different places. So, for instance, SMEs who are doing requirements decomposition and detailed test point narratives can design those narratives or come up with them and then refine and confirm them inside of SDK, use it as part of the design process for the relative route conditions, and then sequence and choreograph a combination of those together. Ultimately, that would increase density and effectiveness and bring down refly rate as well. We've taken this to a couple of additional steps inside of the Teeny toolkit. And so there's a tool that inside the toolkit that, for instance, allows you to take requirements of a particular system and then have the tool step through those requirements in some parametric steps. And it builds up a hypercube of answers of on condition, geometry, total time on condition. So for instance, for this route combination that's in the center of the chart here, if I have a vehicle that has a radar that has requirements that are in the upper left here, and I want to get on condition test point geometry in ranges from 0 to 100 nautical miles and 0 to 360 degrees in azimuth, changes in elevation and range rate. This can go off, and SDK can calculate all of those answers and provide a hypercube, and then spawn tables of the total time on condition for each geometry. So the table on the top is for the geometry as seen. If I turn that route, the on-ship route, 45 degrees and then have it recalculate, it would give you perhaps the table on the bottom that has a different set of answers. So this is something that is typically done in a time-consuming way, with paper processes, and this could be brought down to much quicker with this kind of an activity. Large, complicated exercises that involve multiple maritime vessels, multiple aircraft, multiple radar conditions, and communication conditions and other constraints can be laid out inside the tool. These large, complicated tests are oftentimes difficult and time-consuming to produce, and need a way to be a way to validate their plans. This tool can provide a quick way to do that, and can be a significant risk reduction with that regard. I'm going to move on to the real-time assessment part of this. For a long period of time, AGI has had a way to easily incorporate post-flight data, real-time data into STK and assess what is actually happening with the route as the test unfolds. And that can be brought into a test environment, not just for the purpose of having a display similar to an IADS or other kind of display, but a little bit differently in the sense that having characterized the system as described earlier in these charts, and then having flown, let's say, the first 2 or 3 runs in the actual test, an analyst can go into an offline analysis mode and then scroll back and forth through what just happened and see very quickly whether or not the test articles went through the exact geometry they were supposed to, whether the test points were achieved. So while the test unfolds, you can actually make decisions and communicate with the pilots. You could also go to contingency runs where you want to go back and try one or another run that did not meet objectives. This can have a big impact on refly rate, and we have customers actually doing this. So moving on to post-flight, we build a capability within the tool set to import data. Now, we rely on the fact that most programs already have a way to take their data off of a data pod or from telemetry or both, put it into a database that's indexed, that has unique metric names, and typically they'll have a way to extract that data into CSV files or HDF binary files, or they'll have a way to pull it out into MATLAB and various other ways. So we pick it up from there, and supplementally, this tool can load those files and then turn that data into various objects within STK. So for instance, the time, space, position information gets turned into ephemeris and attitude and covariance in STK vehicles. We turn pointing information into vectors. Any of the data in the data set can turn into scalars, which can then be used as additional decision aid graphics in the tool. Sensor volumes, radar scan volumes, any kind of measurement data can be turned into tracks, position and covariance, and then other sorts of supplemental data like FAA air tracks or AIS ship traffic can be turned into information in the tool. Once all of that is constructed in the tool, inside of STK, then you can perform quick look, flight reconstruction, track analysis, produce verification products, and produce visualization and animations in order to communicate capability and various other things. This relies on a mapping structure that we put together whereby you can map data from the data source, and then those things easily then get turned into the objects in STK. This is an example of a post-flight reconstruct for a flight sciences type quick look, where we've got the route, the aircraft going through its attitude. We have brought in other parameters that typically wouldn't have been turned into STK objects, but things we want to orchestrate with this. So they're turned into scalars and graphed, and it's all interactive. If you click on the graph, it goes to that spot in the route. The graph points can be used to create markers along the route or to colorize the route and to create head-up displays. This is more of a mission systems type flight reconstruct. It's a notional radar flight with notional radar data where the ownership, the target, the measurement data has been brought in. The tracks can be colorized by various pieces in the data set. Within the tool, you can quickly and easily create additional systems analyst visual cues. So, for instance, these are vectors, angles, planes, visual constructs that indicate where the antennas and RF receivers are, radars, etc. It also enables creating combinations of those things that communicate specific things to the analyst. So in this case, subsystem specific operationally significant sensor constructs, such as where and at what angles data collects would be good or bad for certain mission systems, range space, airspaces, threat grouping constructs, etc. For one of the key aspects and one of the key workflows within the tool allows you to visualize track data or measurement data. Again, it can be from radar, electronic warfare data, emitters, EUIR, and that can be visualized as statically or dynamically. You can also wrap it up into different coordinate frames, and anything that's in the data set can be used to colorize the track measurement points in order to assess whether there's correlations between any of those parameters and the error, or just to better understand the behavior. There's a track pick window that lets you inspect the data. You can put as many parameters as you like in there. And ultimately, it provides a way to produce verification products. So you can do track to truth comparison, compare with specs, and then produce scoring results. And we've seen, most places that do that are producing different kinds of measures of performance. We've built workflows within the tool to allow you to produce products such as these. And we've seen folks, doing that with MATLAB and other tools. And this is meant to be for those that don't have those tools, they can do that in here. It also provides a valuable supplement to those tools because when everything's green, it's all good. But when you're out of spec, it's oftentimes difficult to figure out with those tools why you're out of spec. This software excels at being a forensics environment in that case. And we have real examples where folks have used this to understand a system, find problems, inform test planning, cases in which that activity saved them from failure on multi-ship million-dollar flights, cases in which evaluating these things led to informing software development of issues that got fixed in a build earlier than they would have gotten fixed, which rains goodness into the Gantt chart of the ongoing schedule. So all of that really has come down to these kinds of benefits: efficiency of the task force operations, effectiveness and efficiency of the flights themselves. So the efficiency of the operations, the time it takes practitioners to do their job, efficiency of the flights, test point density, refly rates, communicating complex and concepts and issues within the program and with the customer. And we have been out actually implementing these concepts with the JSF Task Force and with other projects within NAVAIR and NOCWD and some other places. Everything we talked about for open air testing also applies just as well to labs, LVC tests, anechoic chamber, hardware in the loop. All of those activities require creating test designs and then that need to be proper and can be analyzed and verified, as well as they produce a lot of data. And the same way that you can reproduce and do post-flight from real flight data, you can do from lab simulations, modeling and simulation, and such. So we're going to move on to a demonstration now, and we're going to pass it over to Cheeto.
All right, Cheeto, whenever you're ready, just press the accept button and it'll make you presenter.
Okay, thanks, Maggie, and hopefully you can see our screen here.
Yep, we can.
So, great. And what I'm going to do is give you a quick introduction to our T&E toolkit. And to do that, I'm going to talk about just a notional flight test, and we're going to focus more on the post-flight analysis of things. And so the flight test will be coming out of Edwards Air Force Base and flying against a couple of air targets on the C-test range off of the West Coast. So let me go ahead. First off, just I apologize if the delay in the go-to meeting with the animation and the response of our 3D window is slow. That's just an artifact of going through the web. So let me first bring up some data. This is the T&E toolkit toolbar, by the way, when you do install the T&E toolkit. So we have a data importer here, and the first thing I'll do is load in some own-chip state data. And we have some sample data here that's just a CSV format. And we first have to give it an identifier and a test ID number, if you like. And then here's that TSP mapping, the time, space, position information that Joe mentioned earlier. I'll go over this sample own chip mapping in a second. I'll go ahead and load this data source. And right now what it's doing is going and creating some ephemeris files for the aircraft that you see here that's loaded into our scenario, and also attitude information for that. And let me go ahead and open this file real quick just to show you what it looks like. This is typical of the data sets that we normally get, usually as a text file or CSV. And you'll notice that this data set has the name of the data element on the first row and then the units on the second row. And you know, the goal here is to make sure that we understand what this data element is with respect to SDK. So we need to do that mapping that we keep talking about. And let me show you a quick mapping of our TSP data. So based on that Excel file that I just showed you, we basically mapped this time in our data source to a SDK property, which is time as well. And then, of course, the latitude, longitude, and altitude for the position. And then we'll use heading, pitch, and roll for the attitude of the aircraft. All right, even with just the aircraft flight path here, we can do quite a few things. One thing we can show you real quick is we could add a data display to our 3D window here, where we can add things like our altitude, we'll do that in feet, maybe calibrated airspeed, dynamic pressure, and even fuel consumed. So all these data sets that I'm bringing in came from the file, and we're just going to go ahead and put that in, and you can see as we animate our scenario, all those parameters will be in sync with our where we are in our scenario. All right, some other things that we normally people like to use is to graph some of this data, and here we can graph some of this additional data that we brought in. For example, back to our calibrated airspeed, we can load in a plot of airspeed versus time. And I think Joe also mentioned that we can also colorize the flight path based on some metric. And in this case, I'll just quickly show you how to do that using that same example for calibrated airspeed. For example, if I'm interested, you look at the path, the flight path between maybe 250 knots to 300 knots, I could add that in as a level, and 300. So if I wanted to show between 250 and 300 in green, and also show less than 250 in red, and then greater than 300 knots in blue. So you can colorize your flight path based on pretty much any metric that you could bring in from a data source like that Excel file. All right, let me turn these guys off just to move on to other things. So again, we were going to mention that this aircraft, this own ship, is going to be flying against a couple targets. So let's go ahead and load those targets now. And we usually call those associated states. And we have target 1. And we'll rename this guy target 1. And give it a 3D model. In this case, we're going to just use a simple F-16. And again, it's an aircraft with that sample TISP mapping, and load that into our scenario. And you'll see the entire flight path again is shown here in yellow, just to differentiate it from the own ship. Let's load in the other target, target 2, and give that a name. And use the same model. All right. So these two aircraft in this scenario actually fly from Point Magoo, not from Edwards. So you may not see them immediately in the display as we're animating. So own ship is flying around for a little bit, and now the targets are shown here. All right. So at this point, you'll notice in our flight paths that you'll see some racetrack patterns. This indicates when they actually are taking some measurements from a particular subsystem like radar or electro-optics, or even EW, electronic warfare, I should say. So to make things easy for us, we have a way to define these flight segments, these runs, if you will. And in this case, I'm just going to choose the radar subsystem here as a run. And we have a file in our training files here called radar runs, and it's just a collection of the start and stop times of these runs. And we'll go ahead and load those in, and they're going to show up in green in our flight path for the own ship. And we can also direct that the targets, target 1 and target 2, are assets that the own ship is going to go against. So we'll load that in as well. And by doing that, we're able to create that link between the own ship and the targets. And let's give that a second to complete. Okay. All right. So if we fast forward, right down here in the timeline view, this is the intervals of those runs that I loaded in just now. And we can look at this again from the aircraft's perspective, from own ship. And we actually have, we can look at the target 2 in another window. We can look at it from the target's perspective here, own ship's perspective on the left. And if I fast forward to run 2, that's what the geometry looks like for run 2. And then if we move over to run 3, that's what we would be seeing for the third run. All right, so given the state information for both the own ship and the targets now, we can do quick looks. And these quick looks are a way for us to get a better sense of what's going on in our scenario here. And for example, I turned on the azimuth elevation and range to the target, and you can very quickly show that. And we have some other things we could do here, like graph our range versus time. And again, we call this quick look, and it's just a way for us to come up with these graphs really quick. And we can also do a multi-graph that shows not just the range to the target, but also the azimuth and the range rate. So again, we weren't doing any track analysis or anything just yet. We were just looking at the geometry, the relative geometry between own ship and target. And this gives us a quick look of what that looks like. All right, so now it's time to load in some track data. And again, this is additional data that we're going to load in. These are going to be the measurement tracks or the measurement data from own ship to these targets. And we have something here called an air tracks, just some notional data that we brought in. And let me bring up the mapping for that particular, for those tracks, just to show you. So we do have, for this particular track file, the latitude, longitude, and altitude of those tracks, and then the measured tracks. And then we also have some covariance information, and also, let's see, that's it. And we have some additional data in here, like the sensor ID, some range quality, and data valid. And we'll talk about the sensor ID here in a second. So this file that we brought in is actually for a multi-sensor kind of measurement. And so there's different types of sensors on there that we're measuring against these two targets. So let's go ahead and introduce our workflows to do that track analysis. We do have these custom workflows built into T&E Toolkit. And you'll notice there's several of them. We're going to look at just a couple of them in the time frame that we have. You'll notice that there's other things in here like track events for weapon systems and creating sensor volumes, and even some ATC data that you could bring in for some ATC assessments. So we're going to focus on this tracks workflow. We're going to go ahead and create a new track object here. We'll just give it a name, and again, that air tracks mapping that we just created. And you'll notice down here is this air tracks pick info, and I'll show that later on, but what that is just a way to click on a track point and get additional information on it. And there's other things here where you can constrain the tracks by track ID or by time, and we're just going to leave that alone for now. So what's going to happen now is that you'll notice that the tracks show up. These are all the measurement tracks for all the runs. You'll see them in white. At the moment, we are in run 2. So we can go to run 3. show you what that looks like. So again, these are all the static tracks for the entire run, for that particular run. But we can show this dynamically and just maybe show the last 2 seconds of that track. And if we animate this scenario, you'll see that it may be a little choppy on your end, but it is very smooth in SDK. So this basically shows the track showing up at the time of the measurement and also trailing for the last 2 seconds. We can also show the tracks at the current time. And if I speed this up, you should see these dots showing up on screen. And these dots are just showing at this particular time in our test. These are the actual measurements happening from ownership. And let me do one more thing here. I'm going to go back to static to show all the track points. And then I'm going to color the tracks, not this static white. We're going to change use a different metric. And I mentioned the different sensors on our own chips. So we're going to go ahead and load in just the sensors, the 3 sensors that we have on board. So we're going to say that we're going to, the sensor 100 is going to be red, sensor 300 is going to be blue, and then sensor 200 is a color somewhere in between. And then if I just select one of those track points, you'll see that this is that pick info that I mentioned earlier for that mapping. You'll see that I'm looking at track ID 1001, which is target 1, and sensor ID 100 is that red track. And then if I go to a blue point, that should be sensor ID 300. Okay? And we can further filter this if I'm interested in only looking at the sensor 100 tracks in this scenario. So there is a filter capability here where I could explicitly select my sensor ID and specify 100. And then I apply that. Now only the tracks that are from sensor 100 show up here. And then I can also further constrain that and say that I'm only interested in looking at our target 1 and not target 2. And we'll go ahead and do that. And now we only have the tracks for target 1 and no longer for target 2. So this is where we normally take a look at the track data and determine, you know, how good is my measurement compared to my truth data, which is our target 1 TISP data shown here. One more thing I'd like to show before I continue on here, but I'll leave this up for a second. So to do that comparison, I'm going to first promote this track so that it creates an aircraft object in SDK. And you'll see here, it's shown here as tracks measured. And basically then we can use aircraft to aircraft to determine how good our measurements are to do that track comparison. Let me go ahead and add in here another connect line between own ship and that tracks measured object here. Let me select that in here first of all, create that connect line. So now we can see that line, that white line, 2 white lines going to target and the measured track. We can now do the track comparison, and that's another workflow here, and I'll try to do this real quick. Just select the tracks that we just created. The own ship is XF123, and our truth object is target 1. Our measured object is tracks measured. We're going to use the northwest up or whatever reference frame that you have your data measured in. And we're also going to use a time interval, in this case, the run 3 that we have. I'm going to click OK. And so now at this point, it's going off and making those calculations for example, the slant range to the track versus the slant range to the target, and then what differences that between those two. It also calculates things like the azimuth and the elevation angle and the differences between the truth versus the measured object. So here we have that completed, and we can go straight to our calculator, which gives us our evaluation parametric. Like I mentioned here, we were using slant range and elevation and azimuth. So this data has, for this particular run, the minimum slant range is about 56.9 to about 101.7. And we could certainly filter and say, what if I'm only interested between 80 and 90 nautical miles? And I can refresh this table, and it'll give me my measure of performance down here, my minimums, maximums, average, standard deed, and root mean square. And we can also create a graph that will plot the slant range difference in feet versus our truth slant range in nautical miles. And you'll see something like this. And let me just zoom in real quick just to show you here. What's going on here is basically all the tracks in versus our slant range here. So these red lines represent our spec lines for that range. For example, this spec line is plus or minus 250 feet for the range of 60 to 70 nautical miles. And this spec line is plus or minus 400 feet between 70 and 80 nautical miles, and so forth. And what's nice about this plot is, again, we can go in and click on a point that's, say, outside of our spec line, and see what condition that was that created that out of spec condition. Or if we're really more interested in a group of points, we can go ahead and create these track events or event markers and rope off a bunch of these points that are out of spec. And then in SDK, or in the 3D window, I should say, those points will show up as these event markers on our flight path, and that could give us further clue into why we were out of spec for that particular track point. All right, I think I'm almost out of time here, so there's one more thing I'd like to show. Going back to our tracks workflow here, I didn't mention that we did have a covariance tab, and we had covariance data we loaded in, but we're just going to go ahead and load in this. So basically what we see here is our covariance, position covariance ellipsoid, and let me move on to a particular point in time. So if I step through this particular one, inside, if the measured track, or I'm sorry, if the truth object, in this case target 1, is inside the ellipsoid, then it stays green. And then if I kind of step through this one step at a time, there is a point where we go outside of the ellipse, and let me speed that up just a tad. It turns red when the target is outside of that ellipsoid, and that's another way to visualize the measurements of my the measurement track data that I have. So I think that's it for the demonstration. I'll send it back to Joe.
Thanks a lot, Cheeto.
Great. I'm just going to make sure we switch presenters here.
Thanks, Maggie. So at this point, we're going to go to questions.
Yeah, looks like we actually have a couple right now. First question is, how long does it take to get up to speed with TETK?
Okay, so again, I'll mention that the test and evaluation toolkit is a bundle that includes the overall STK systems bundle, Aviator, Aviator Pro, as well as a couple of other modules, and the rest of the T&E capability. We have a set of standard training courses that are out on the AGI website for SDK training. There's fundamentals training, different levels of fundamentals training. And then we have a set of training that is oriented specifically to test and evaluation toolkit and a series of vignettes that we use for that training, both for planning and analysis. That material has not yet been put up as standard training on the website, but if folks are interested, they can email us and we can send that to them and walk them through it. Many times when people buy T&E Toolkit, we're also engaging with them to do a little bit of technical interchange to evaluate what their particular needs are, so that we focus the training for them.
Great, thanks. Next question is, my data is in binary format, not text or CSV. How do I bring that data into SDK?
Okay, yeah, thanks. I'll go back just real quick here and bring up this screen as a backdrop for this question. I mentioned before that there's this data importer, and Cheeto showed it and showed the mapping for it. It's set up so that it can read CSV data with a header that has the metric name and the units in the first two rows. It can be as many columns as you like. We've done files that are as many as 1,000 columns, and even ones that are 1 million lines. Some places that we've gone, because of the size of those files, they've been binary. So for instance, they're in HDF format. And we've found that sometimes the header of the binary file is special and contains certain information that they would like to use. So we do have a generic binary reader in the form of the one we've written already to read HDF. But it's likely that if someone has binary data, we would, again, interface with them and perhaps write an additional reader to meet their needs, which is pretty low-hanging fruit and not all that hard to do.
Awesome, thank you. And who are the current users of the T&E Toolkit?
So I mentioned earlier that we have several folks that we've worked with already. We spent a few years out at the Integrated Test Force working with the JSF test team there. That's ongoing, although they're in a lull period now between their major builds, to start back up, I think, sometime after October or November. We also have done work for the F-18 Advanced Weapons Lab out at China Lake, and then a couple of other projects down at NavAir at Patuxent River, as well as other contractors here and there.
Great. And another question we have is, can you have multiple ownerships and targets in the same scenario? Yeah,
so that's, let's see, that one says, I think it says ownships. So yeah, so essentially the systems under test, or otherwise known as an ownship, you can have as many of those in the scenario as you like. And that's one of the big benefits here, is that this tool allows you to load the data for each of those aircraft, and it syncs up the time-specific data very quickly. That we've found people telling us in test teams that that's many times a long pole in their process to bring disparate data sets in from different systems under test and sync those up so that they can go and actually do their analysis. That's something that's done very easily in the tool. You load as many of those different ownership sets of state data that you want, and then you load other data sets that go with each of those systems under test, and it appropriately aligns that data with each of the systems. So, and then that same thing goes for the targets in the scenario.
Great. Two more questions here. Can you bring in aeronautical charts and aerospace regions of the test ranges?
Yeah, so you may have noticed when Cheeto was doing his demonstration that there was a background map that was updating. If you're online, that's a streaming set of data and terrain. that a similar situation can be set up for folks who are not online, as well as any kind of map data. So aeronautical charts that show the extents of the test region, and various other backgrounds can be put within the system and draped on terrain.
Great. Last question is, can you use GPS data for TSPI?
Yeah, so any kind of state data can be used, as long as that data contains position and time-oriented, sequenced position data. And we can take position data, position and velocity, including orientation, the attitude of the vehicle, and including covariance. So that would be the same thing, would go for GPS state data.
Great. That's all the questions that we have. Do you mind going back to the slide that talks about all the tools and products that we talked about?
Sure.
Awesome, and I can let you talk about that if you'd like.
So again, it says products mentioned, and I talked a little while ago about that the test and evaluation toolkit is really a bundle of the T&E capability that's been built on top of the overall SDK toolset. The training, as I was saying in answer to the question that was asked, is out there at this link. If any of you folks have additional questions or comments or would like us to show you anything further, you can contact us through info@AGI, and I've also put my Cheeto and my email addresses on here. You can contact us directly. There are a whole series of capabilities in the tool that we really didn't get a chance to show you today. So if anyone would like a more detailed presentation, we could do that as an additional GoToMeeting, or we could also come on site and work with people directly.
Great. Thanks, guys. And thank you to all for joining the webinar. For those questions that we didn't get to, we will be answering those individually after we sign off, because I see that we have a few now. Make sure to join us for our next webinar on model-based systems engineering on September 26th. See you next time.
Thanks.